shifts of functions. So we're going to use one of our basic functions here, the absolute value function. You could use any of them, it's just the one that I chose here. And that's our basic function. And then we're going to introduce one of our linear operations, subtraction of a constant, in this case 3. Now, why is it that that creates a vertical shift as opposed to a horizontal shift, which we'll look at next? Well, here's an example. If I were to evaluate the original function at any x value, I would perform the operation, get the output. Now, if I were to evaluate g at the exact same x value, now the reason I'm using the exact same x value is because if this is truly a vertical shift, as we said, then it should go up and down, which should be a change in the y values. It should have absolutely no effect on the x values. So I'm using the same x value in each one. Now, the interesting thing to note here is that at first, this transformed function g does exactly what the original function f did. But then, afterward, we make a change. So we're taking the original y value from the function, and we're subtracting 3 from it. That's why it creates a vertical shift, because it's going to take the same x value and produce the same y value, at least at first. Then it's going to make that alteration to the original y value. Now, I happened to use the x value of 2. On the graph, that would be the original point 2, 2. And produced a new ordered pair for this new function. I could have used any input value in the domain of the function. Let's try, for example, f of -1. Well, the absolute value of -1 is +1, of course. I then come to this transformed function, and I use the same x value. Again, we're using the same x value because a vertical transformation will affect the y coordinate. It will affect the up and down. So x is still the same. Now, just like before, I'm going to do the same thing to start and produce the same result to start. But then I'm going to make my change afterward. That's why the addition or subtraction happening after the absolute value operation creates a vertical shift. It takes all of the original output values and then subtracts, in this case, subtracts 3 from every one of the y values that was originally produced in the function. Now, we can see this visually by taking the graph of the original function f of x, which has, well, let's use the 2 points that I mentioned before. I used 2, 2, and here -1, 1. Now, I could do this with multiple points on the graph, and in practice we will. G of x then, we'll graph this in a different color. G of x should be a vertical shift down 3 units. Now, as we saw from these 2 points, this in particular, because it happens to be on the board at the moment, it's the same x value, but the y value is 3 lower. We saw the same thing with this. When our input was 2, the output value to g of x was -1. Because literally, the point has moved down 3 spaces. Every point moves down 3 spaces. So this point here will move down 3 spaces. And so on. And we get the same graph, but in a new position, 3 spaces downward from the original. Now, vertical shifts, and as we'll see moving forward, vertical transformations in general tend to be easier to work with because in order to affect a y value, you must first produce the original y value. And then you can make your changes to it. So how about horizontal transformations, horizontal shifts in this case? Well, let's take a look at a different function. The symmetry of the absolute value graph makes the absolute value just a slightly more annoying thing to work with for horizontal shifts. So we'll use something slightly friendlier. This time let's try the square root function. Now, according to the definition in the PowerPoint, if we want to have a horizontal shift, it needs to occur inside. Think function composition. It needs to occur inside the function operation. The square root of x plus 2. Now, by definition, this is supposed to produce a horizontal shift. That means that the y values are unaffected. That makes this a little bit more interesting, of course, because it means we have to kind of start with a y value. So for example, suppose I want to produce the y value of 3. Well, I can take my y value of 3, put it in, and then I can solve this and what I get is the x value that produced that y value. To write this in function notation, f of 9 equals 3. Now, suppose I want the exact same output value, because again, a horizontal shift should affect the x coordinates, but since we're moving side to side, it should have no effect on the y coordinates. So we have the same y value, but we're going to end up with a different x value that produces it. We're still going to have to square to get rid of that radical. We're still going to get 9 at first. but we then need to make a change by solving for x. So much like we saw with the vertical shift, we start with the same x because we know x is not supposed to be affected. And we see what happens. And what ends up happening is in the transformation function, it produces the original y value and then makes an alteration. This is exactly the opposite. Here, since this is supposed to be horizontal, we start with the same y coordinate. We even then, in solving, get the original x coordinate. But there's an alteration there. Now here's the big difference between vertical and horizontal shifts. And as we'll see later, vertical and horizontal reflections and stretches as well. In the vertical shift, if there was a -3, we actually subtract 3. But here, it's a +2, and we need to undo it with the inverse operation. So despite the fact that that is a +2, the x value is actually 2 smaller than the original. That definitely makes for an interesting little twist there. For that reason, horizontal transformations are never quite what they seem just at a glance. That does say a +2, but it doesn't go to the right. It actually goes 2 spaces to the left because to undo the +2, we have to use a subtraction of 2. That results in our x value being 2 smaller than it was originally. That's a lot to swallow. Which again is part of the reason why there's a video for this, so you can go back and rewatch it. But let's try another one. Let's do another ordered pair here. This time, now we can choose any y value in the range of the function. The range of the square root function is 0 to infinity, including the 0, so we can choose any non-negative value here. We just did 3. Why don't we try something more like 5? Now, again, we will have to solve for x, which of course is not that big of a deal. I mean, we don't really, I suppose, need to actually work this out to know what the x value is. That's a fairly obvious relationship. But again, it's about seeing what happens here and then seeing the same thing happen here with an extra adjustment. So let's try again. The same output value, 5. And again, we're going to see the same thing being done. And the same value produced at first. But after we produce the same value as the original function, we come in and we make our alteration. And again, we produce an x value that is 2 smaller than the original. So, let's take a look at the graphs. Now, the original function, f of x equals the square root of x, goes through the point 0, 0, 1, 1, 4, 2, and, as we saw in our first ordered pair, 9, 3. Now, when we found ordered pairs for g of x, we found that the x-coordinates were 2 smaller. So when we had an output value of 3, whereas the original function had a 9, the transformed function had x equals 7. Now, the other point we used was a y value of 5, and the x values were quite large, 25 and 23. But the idea is this. Again, that this point was moved 2 spaces to the left. And while we're not graphing the other one, we had the same situation, where the x value was 2 spaces to the left of what it was originally. So if we do that with other points on here, we can produce the rest of the graph. And 2 spaces over. And this is the graph of g of x. Every x-coordinate in every ordered pair shifted to the left 2 smaller than the original. Shifts are the easiest of the transformations, and because of that, they're usually the first. Now, one thing I do have to caution you with horizontal shifts is there's a tendency to want to look at that and go, oh, well, if it says +2, then we really go -2 to the left. Horizontal transformations can be a little bit funky. As we saw, in order to get the new x value, we had to undo the operation in there. As we'll see going through the other transformations, there are other operations that may be there. A coefficient in front of the x, for example. And that can make things a bit more interesting. So please try not to think of that as just using the opposite of whatever you see there. It's not that simple all the time. We will see examples of that in future videos once we get the other transformations going.